Hey students, welcome back. This is Torres, elbow bump. How are you? Are you doing okay? Is your family okay? Remember, if you need anything, send me an email. Even if you just want to send me an email to say hello, that would mean so much to me, and it'd give me a chance to reach out to you personally. So I'm going to be looking in my mailbox to make sure that you guys can, you guys reach out. I would really like to hear from you. So lucky you get to hear my voice for another lecture, but the best part is we're going to be learning about the Central Limit Theorem. Yay! Teaching the Central Limit Theorem is one of my favorite topics to teach. Huge fan. So let's get going. Since the beginning of the course, I've tried to emphasize that the shape of the distribution is very important in statistics. If you have a normal distribution, then you can predict the probability of the event just because we know that approximately 68% of the values will lie within one standard deviation, approximately 95% of the values will lie within two standard deviations, and approximately 99% of the values will lie within three standard deviations before and after the mean. But what happens if the distribution is not normal? There's several things you can try, but in this course, we concentrate on using the conditions of the Central Limit Theorem. If you can apply the conditions of the Central Limit Theorem, then you can meet the assumption of normality. In other words, if you can apply the following conditions that I'm going to show you, you can assume that data is normal. In statistics, we start by asking a question about a population. For many reasons, you may not have access to an entire population. Perhaps the population is too large. Perhaps your study doesn't accommodate for that type of sampling. So instead, what we do is we take a sample of the population, we gather information about that sample, and then we apply what we've learned from that sample to the population as a whole. So with that said, let's look at a very, very tiny population. And the population we're going to start talking about is the children on this screen. Okay, so if you notice, there are 5 children on the screen total. And I can look at this and see that there's 3 little girls and 2 little boys. And if I wanted to know what the percent male is, I would say that 2 of the 5 boys, so 2 divided by 5 is 0.4, and 0.4 is the decimal way that we can show 40%. Now, if this was the total population, very tiny population, we know the truth. We know that the truth is that there are 40% boys in this. But what if we can't see all of the population? We only can use a small sample of this small population to make inferences. What happens then? Well, if I were to go ahead and draw a random sample from my population, let's just say that I decide that I'm going to take random samples of 3 and of the 5 children. So of those 5 children, I'm going to pretend to put their names in a bag or pictures in a bag, right? And then do a random sample of 3. And I record the percent of the draws that are male. Well, there's only really 3 possibilities here, right? I can draw a boy and 2 girls, okay? I can draw 2 boys and a girl, or I can draw 3 girls, right? The proportion of the sample is this little p with this little arrow at the top, and this is pronounced p hat, like a hat that you'd wear on your head. So p hat. So if we're showing the proportion of a sample, we're going to notate that as p hat, and that's 33%. The notation here are 2 out of the 3 people in the draw were boys, so that's 2 out of 3. So the p hat is 66.66666. I'll show you that here. So 2 divided by 3 is, see all these 6s? So we just decided to round up to 67%. Okay? Another thing that could happen is I could draw 3 girls, in which case there are no boys in this draw. So p hat is going to be equal to 0. Okay, so p hat, so I can get 1 out of 3, 33%. I can get 2 out of 3, which is 67%, or I can do a draw and none of these children are boys, okay? So I have one population proportion, which is 40%, which is the truth, but I have many sample proportions. Many things can happen from that. Let's say I do this 10 times. So here you see that I got 0% boys one time. Here I got 1 out of the 3 boys 6 times. And I had 3 draws that had 2 out of the 3 boys, the 3 possibilities, right? Let's add up all these proportions and take the average. So here I'm going to calculate all the sample mean proportions. I have 1, 0, so this one right here is the 1. I have 6 33%, and right here are my 6 33%. And I have 3 67%, and right here I have the 67%. If I divide that by 10, which is 10 draws, then I get my proportion is 0.399999, which is pretty much 40%, right? 0.4, 40%. So the sampling distribution has a mean of 40%. The samples together, once I take the mean of those samples, it's 40%. And this is the same as the true population proportion, 40%. So the truth, when we looked at all the boys and girls, we knew that the truth was 40%. 2 out of the 5 children were boys. So that brings us to our first big idea. As the sampling proportion increases, what you'll start to notice is that the distribution will become normal. So if here's my graph that I had from the previous slide, notice what's happening here. This distribution is starting to take the shape of a normal curve. You see my little comment dancing around? I'm trying to get it to sort of follow the shape of the normal curve. The mean of the sampling proportion will be approximately the same as the true population proportion. So in other words, if I have my population and I take a sample and I calculate the proportion, and then I take another sample and I calculate that proportion, and I take another sample and I calculate that proportion, right? And I do it over and over and over again. And then I take all my newly calculated proportions and I average them out. I take the mean of those proportions. Then that average that I've calculated using the sampling proportions will be approximately the same as the true population proportions. So that's what it says, the mean of the sampling proportions, the proportions that you took as part of your samples, as your samples, will be approximately same as the truth. The truth lies within the population proportion. In order for you to be able to apply the central limit theorem, there's very strict conditions that must be met. And I'm going to go over these in more detail. The first condition is that the sample has to be collected randomly and every trial is independent of one another. The next condition is you have to have a large sample. So the condition that you're looking to meet has to appear at least 10 times within the sample, and it has to fail 3 times within the sample. Finally, you must have a large population. The population must be at least 10 times the size of the sample. So let's unpack these a little bit more easily. First, let's talk about checking for independence, okay? First of all, the sample has to be collected randomly, has to be at random. And each trial has to be independent of one another, meaning that the odds of being selected, right, a participant or an object or whatever it is being selected does not change from one sampling to another. Let's look at an example that might bring you nice warm fuzzies from when you were a little kid. Okay, remember when we studied probability as a kid? You probably at one point dealt with a little pouch that had marbles in it. So this is my attempt to draw a pouch with marbles in it, okay? So consider you have this scenario, okay? Here is a pouch, and there are 10 marbles total, right? So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 marbles total. In here you have 9 blue marbles, and then you have this 1 orange marble. Okay, so let's think of the first draw here. Event number 1, we'll call it. If you were to draw one marble from this bag, the odds of drawing an orange marble is 1 out of 10, right? So you have this one orange marble that if you close your eyes, you put your little hand, little paw into the pouch, and you draw out one marble, there's a 1 out of 10 chance that you will get an orange marble. Let's say you did that. You did event number 1 and you drew a blue marble, and you do not replace the blue marble, so you leave it out of the pouch, then the odds of drawing an orange marble changes, and it changes to 1 out of 9. Now there is no longer a 10% chance of drawing an orange marble. Now in event 2, there is 11.11% chance of drawing an orange marble. So the probability of event 2 was directly affected by the probability of event 1. Here you can see just a summary of this again. Originally, event 1 had a 10% chance of drawing the orange marble, but then the chances changed for the second event. Had event 1 never occurred, then event 2 would not have been affected. So event 2 was directly affected by event 1. Again, the probability of event 2 was affected by the probability of event 1. In order for the condition of independence to be met in the central limit theorem, this cannot happen. The odds have to remain the same for each draw, so the marble would have had to have been replaced for each one of the draws. Let's look at the next condition, the condition of a large sample. For the purpose of applying the central limit theorem, we'll consider a sample size to be large when the proportion of successes is greater than or equal to 10, and the proportion of failures is greater than or equal to 10. What does that mean exactly? When we talk about the successes of the sample, that describes the proportion of the sample that has the characteristic of interest. We can calculate the proportion by multiplying the sample size times the proportion, and we look to see if that number is greater than or equal to 10. The failures describe the proportion that does not have the characteristic. So everybody in the sample that was not a success. You can calculate this by subtracting the proportion from a whole, then multiplying it by the sample size. If that number is greater than 10, then you have met the condition. By the way, another way of expressing failures is Q. Another way to express failures is by the lowercase q. Q is equivalent to subtracting the proportion from a whole. It's the same thing. The sample size multiplied by Q is greater than equal to 10 is a different way to express failures as well. Ultimately, this represents the same thing. Failures are the remainder of the sample that does not have the characteristic of interest. So basically everybody else except the successes. So again, if we have at least 10 successes and we have 10 failures, then the criteria for this condition is met. The final condition that must be met for the central limit theorem to apply is that there must be a large population. The large population can be defined by the population size being at least 10 times greater than the sample size. So let's try to check the conditions for a real problem. Okay, so it says 78% of all lab mice can make it through a maze. If 600 randomly and independently selected mice attempt the maze, what is the probability that more than 80% of them will make it through the maze? And it says, check that all requirements for the central limit theorem are met. Okay, let's try the first one. So the first condition is that the sample has to be randomly and independently drawn. That is just stated in the problem. So we know that the first condition is met. Check. The next condition deals with successes and failures. Let's look at successes first. We want to know, is there a possibility that if we use the parameter that we're given, 78%, which is right here, more than 10 mice will meet the criteria? So if we took our calculator, and I'm going to go ahead and just kind of drag it over here real quick so you can look at what I'm doing. If we take the criteria, or if we take the 600 mice and we multiply it by the parameter that we're given, 78%, we expect that 468 mice will meet the criteria. Since 468 is greater than 10, we meet the criteria. Let's look at the second part of this condition, which is the failures. If we expect 468 mice to complete the maze, then we would also expect that 132 of them, the difference between the 600 mice and the 468 successes, to not complete the maze. That would be the failure. Since 132 is greater than or equal to 10, or the second part of the condition, the failure part of the condition, is also met. Another way that you can, if you wanted to figure out failures mathematically, you would just take the proportion parameter. So you would take the 78%, right, and subtract that from a whole to get 22% or 0.22, then multiply it by your sample, and you will also get 132. So right now we know that 132 is greater than or equal to 10, so the second condition is met. Check. So just to review, here we have the calculation of the successes, which is 600 multiplied by the 78%. This is the proportion, the parameter, because it's talking about the population. And if I express 78% as a decimal, I get 0.78. When I multiply these two together, I get 468. 468 is greater than or equal to 10, so the condition is met. Same with the failures. If I expect 468 to be the successes, then the difference would be the failures. You can subtract that if that makes the most sense to you. Another way to do it mathematically would be to subtract the proportion from a whole. So 1 minus 0.78 is 0.22. Then multiply it by the sample size and you will get the failures. Again, it's 132. Since 132 is greater than or equal to 10, that criteria is also met. The third and final condition of the central limit theorem is the population size condition. The population size must be at least 10 times larger than the sample size. So big N has to be 10 times little n. The population here is all lab mice, which is basically millions of mice. The sample size n is 600. So if we multiply 600 by 10, we get 6,000. Since millions, and I just put down a million here, but since a million is greater than 6,000, then the condition of large population size is met. Check. So that's all you do. You just check each condition to see how it works out. Let's do one more example. I want to talk about this one because I think it's really important with everything that's going on that we really think about our elderly population. I've been watching on the news that so many of the nursing homes have been hit hard because someone went in there with the virus and are very susceptible to this. I think of my own mom who is 88 and how I worry about her being okay with the virus. And I also think about all the other things that happens as we get older. When I was looking for an example, I came upon this one, which is really looking at muscle mass conservation in the elderly. It said that by the time you're born to around the time you turn 30, your muscles grow larger and stronger. But at some point in your 30s, you start to lose muscle mass and function. The cause is age-related sarcopenia, or sarcopenia with aging. Physically inactive people can lose as much as 3% to 5% of their muscle mass each decade after age 30. Even if you're active, you still have muscle loss. There's no test or specific level of muscle mass that will diagnose sarcopenia. Any loss of muscle matters because it lessens strength and mobility. So it lessens how strong you are and how much you can move. Sarcopenia typically happens faster around age 75, but it may also speed up as early as 65 or as late as 80. It's a factor in frailty and the likelihood of falls and fractures in older adults. And I got this from WebMD on April 1st. Okay, so basically if we can have our seniors engage in something that is going to help their muscle mass, then they're less likely to fall or fracture them or fracture bones, especially like hips, which is just horrible when an elderly person fractures the hip. So let's look at this example. 83% of all elderly patients maintain muscle mass when participating in group exercise classes. If 1,548 randomly and independently selected elderly patients participate in group exercise classes, what is the probability that more than 90 of them will maintain muscle mass? I want you to check to see that all requirements of the Central Limit Theorem are met. Okay, so you're going to note that. So if this is a great time for you to pause the video and see if you can do this. Remember, the 3 conditions are: 1, that the sample was randomly and independently selected; 2, that the numbers of successes and the number of failures are greater than or equal to 10; and 3, that the population is at least 10 times larger than the sample size. So hopefully you had a chance to try this by yourself, but let's see what we got together. Okay, so the first condition is that the sample has to be random and independently selected. So it says in the problem itself that the sample was randomly and independently selected. So that condition is met. Next, we're going to check that the sample size is large enough, and we're going to check for successes and we're going to check for failures. So if I have 1,548 seniors in my sample, then if 83% should maintain muscle mass when participating in group exercise classes, and that's the parameter that I was given, then I would expect that of the 1,548, that approximately 1,285, right? Because you can't have 84th of a person. So I'm just going to go ahead and round that to 85, will maintain muscle mass. And since 1,285 is greater than or equal to 10, then it meets the success criteria. I could just go ahead and subtract 1,285 from 1,548 and get the next number. But let's just go ahead and do it mathematically. If I take the 83% away from one whole, I get 17%, and I can express that as a decimal as 0.17. If I multiply the 0.17 by the sample size, which is 1,548, I will get that approximately 263 people will not maintain muscle mass. Since 163 is greater than or equal to 10, I have also met the criteria for a large sample. Finally, I need to have a population size. I know that there's millions of elderly people. If I know that there's millions of elderly people and I just need 10 times the sample size, well, if I multiplied 1,548 by 10, I would get 15,480. Millions is much greater than 15,480, so my large population size condition is met. So what's the big idea? As I've been saying, when the distribution of the data is normal, you can predict the probability of an event. The next big idea is that if the conditions of the central limit theory are met, then the assumption of normality is also met, regardless of the shape of the distribution. So even if you check the assumptions in the typical way that we've been doing it, and you are getting skewed data, we still know that you can assume normality. So that's it for today. With that said, don't forget to check your emails, check Blackboard, do your homework, and subscribe to this channel. Even better, hit that notification bell so you know when there are new videos for this course. Okay? This is your teacher, Torres, saying stay safe, and I will be waiting to give you your virtual elbow bump in the next video. Ciao!